My name is Sean McCartney, and on behalf of my colleagues from the ARSET program, I'd like to welcome you to the fourth and final part of the ARSET training on Earth observations for disaster risk assessment and resilience. Today's webinar will focus on operational applications of remote sensing for disaster management. We've invited our colleagues, Michael Chapman and Dr. Joseph Green, from the Pacific Disaster Center to describe the data, applications, and strategies they use for disaster risk reduction, response, and relief operations. They will provide an overview of the Pacific Disaster Center, their cutting-edge decision support platform, DisasterAware, and how they incorporate NASA satellite data and products into their workflow. I will now turn the presentation over to Michael to learn more.
Aloha, I am Michael Chapman, Disaster Management Specialist and Response Lead for the Pacific Disaster Center at our headquarters in Maui, Hawaii. My colleague, Dr. Green, Acting Director of Applied Science, and I are here today to provide an overview of PDC, our all-hazard early warning and decision support platform called DisasterAware, and some examples of how PDC applies remotely sensed data for informed decision-making during planning and response. For those of you that are not familiar with PDC, we have been around for 20 years and are an applied research center under the University of Hawaii. Please don't be confused by our name, as we don't only operate in the Pacific, but globally. PDC has worked in many places around the world, as shown on this map. And our global mission is to provide evidence-based research, applied science information, and cutting-edge technology solutions for more effective disaster risk reduction policies, practices, and humanitarian assistance and disaster relief operations in the Asia-Pacific region and beyond. PDC works hand in hand with partners around the globe to reduce disaster risk, prevent losses, and protect lives. Our partners are not only located in the United States, but internationally as well. On the screen, you can see some of our United States partners. And here, you can see that our partners around the world include multiple levels of decision-making, such as international, regional, state and local, as well as non-governmental and non-traditional humanitarian assistance and disaster management practitioners. And our audience also includes the public, which could be the international community, friends, family, etc., as we provide a variety of applications to help people monitor disasters and stay safe. With over 1.7 million users, our DisasterAware platform is used by humanitarian assistance and disaster relief practitioners around the world, and offers the largest collection of scientifically verified geospatial data and modeling tools to help assess hazard risk and impacts worldwide. We will now share with you a quick video overview of DisasterAware. Disasters happen fast. We alert you faster. Developed by the Pacific Disaster Center and recognized internationally for its continuous innovations, DisasterAware offers you the most comprehensive disaster risk and early warning solution so that you can make informed decisions and take action before getting caught in a crisis. Monitor hazards around the world from anywhere and at any time. Be alerted to hazards in your specific location through text and email notifications. Access real-time observations and hazard forecasts. Utilize scientific projections to see the potential impacts of a hazard.
Our system requires no specialized expertise. It's that easy to use. For example, a tropical cyclone forms and you receive a text message alerting you about the situation, including the direction and scope of impact. In DisasterAware, you will see its current location and where it might go next, who and what might be impacted and impact severity, how many people, homes, critical infrastructure, how many resources will be needed to provide humanitarian relief such as water, food, and shelter.
As the tropical cyclone progresses, DisasterWare can help you answer questions like, what are the latest updates? Has the path and scope of impact changed? What is the current damage? What is happening on the ground? What is being shared through social media from the impacted area? Are there any other hazards in the area I should worry about that may compound the problem?
DisasterWare helps keep you informed during a disaster and also helps you plan and prepare by providing information such as, what is my risk? Where and what types of hazards have occurred in the past? How severe were they? Where are the nearest shelters, evacuation zones, etc.?
Whether you are a disaster management professional or just want to keep you and your family safe, DisasterWare can provide you with as little or as much detail as you need to keep informed and respond effectively. Don't let disaster catch you off guard. For more information on DisasterWare from the Pacific Disaster Center, go to www.pdc.org. To gain access to DisasterWare, please visit eamops.pdc.org, which is the URL shown on the screen, and select the Request Access option. The example shown below depicts hazards being tracked around the world via DisasterWare, overlaid with NASA's iMerge rainfall data. Log on to DisasterWare today to access the latest updates on hazards around the world, as well as over 4,000 layers. PDC is also a member of the International Charter for Space and Major Disasters. Through this collaboration, PDC is able to support the international remote sensing community through hazard updates, data and analysis, as well as through value-added products derived using remote sensing data. For more information on the Disaster Charter, please see disastercharter.org on the URL below. The examples on this slide demonstrate how PDC has leveraged NASA iMerge rainfall and global landslide nowcast data to conduct exposure analysis and derive products to inform decision making. These layers and products are made available through DisasterWare in support of the international response community. The exposure depicted on the right was derived using PDC's all-hazard impact model called AIM, which provides scientifically reliable information about the potentially exposed built environment and vulnerable populations. This example demonstrates how NASA FIRMS data was leveraged between flyover perimeter updates during the July 2019 Central Maui wildfires. These remotely sensed data were especially useful during times when it was not safe to conduct a flyover by helicopter. Combined with the flyover information on the right, as well as the information on the left when the flyover perimeters were not available, this information helped provide a continuous support for situational awareness during this event. As demonstrated on this slide, preliminary impact and hazard zone observation data from PDC remote sensing partners are often incorporated into DisasterWare as both layers and products in support of disaster response activities around the world. Remote sensing is extremely valuable for conducting preliminary damage assessment in hard-to-access impacted regions. The example on the left shows remotely sensed preliminary damage data for the September 2018 Sulawesi, Indonesia earthquake and tsunami, available through DisasterWare. And on the right is an example of how remotely sensed flood zones were combined with PDC's AIM exposure model to estimate population exposed, as well as potential humanitarian needs based on international standards for basic water, nutrition, shelter, human waste, and refuse requirements. PDC also applies these data in a more traditional sense through pre- and post-impact imagery comparisons and analysis. On the left is an example of how satellite imagery was used to identify internally displaced persons following the 2015 Nepal earthquake. On the right is a pre and post impact imagery comparison for Hurricane Irma in 2017. I will now turn the presentation over to Dr. Joe Green, who will provide a brief overview of PDC's risk and vulnerability assessment capabilities and how to apply them.
The objective of PDC's risk and vulnerability assessment is to provide stakeholders the support necessary for evidence-based decision-making. This is accomplished by combining hazard exposure data, such as the previously mentioned iMerge and landslide data, with socioeconomic, infrastructure, and governance data. The assessment provides a comparison of the likelihood of experiencing negative impacts given exposure to natural hazards. There are many reasons to conduct a risk assessment. In the forefront of these reasons are that natural disasters have the potential to exacerbate vulnerabilities and social inequalities, as well as place unbearable strain on local, regional, and global economies. Risk assessments provide one way to measure and break down disaster risk into disaster risk reduction actions. To provide actionable, rapidly comparable information to stakeholders, the RVA, or Risk and Vulnerability Assessment, leverages a composite index approach. This approach combines multiple variables into a single value. Variables are selected based on an underlying model designed to represent themes relevant to disaster risk. It provides a score on a scale of 0 to 1, with 0 being very low risk and 1 being very high risk. This approach allows users to examine each piece of the data in the model. Presented here is a graphic describing the underlying model in PDC's risk and vulnerability assessment. Risk is envisioned as being composed of exposure to a hazard, the vulnerability of the population, the coping capacities of that population, as well as the disaster management capabilities. Each of these can be further subdivided into subcomponents that, when combined, approximate the components of risk. Subcomponents are then composed of indicators or individual data sets. The results of the risk and vulnerability assessment support a culture of data-driven decision-making that supports decision makers in assessing risk, identifying drivers of risk, and allocating resources. Using the risk and vulnerability assessment as a foundation for understanding of disaster risk can facilitate communication of complex information and underpin narratives about disaster risk and risk reduction. By leveraging the composite indicator approach, complex information can be rapidly distilled into actionable information, comparisons can be simplified, and a big picture summary can be presented. Incorporating a risk assessment, such as the RVA, into a situational awareness tool like EMOps provides benefits beyond either in isolation. By having all information in a single identical display of relevant information, we gain the ability to validate, support, and extend the utility of hazard information, as well as risk and vulnerability data, allow a multi-stakeholder approach to rapid prioritization and/or allocation of resources to affect positive outcomes within groups deemed vulnerable, and to facilitate decision-making across sectors. PDC conducts risk and vulnerability assessments at a variety of scales. Our two most common are at the global and subnational level. The global is designed for country-to-country comparisons. The data sets are selected based on the concepts we are measuring, as well as data availability at the global level. The subnational assessments are data and context driven. These are done in conjunction with in the country with partners and stakeholders. This slide is an illustration of how RVA and hazard information can be combined to provide decision support. In November 2016, Hurricane Otto formed in the Caribbean and threatened Nicaragua. By November 23rd, it had strengthened into a Category 3 storm. PDC had completed a subnational risk assessment as part of our ongoing NDPBA project. The data and analysis compiled for Nicaragua was used for planning and prioritization of resources. Otto made landfall on the 23rd of November. A magnitude 6.9 earthquake struck offshore on the 24th of November. The RVA analysis provided to be a useful tool for prioritization of resources during this unprecedented series of events. What it allowed stakeholders to do was to look at the impact or potential impacts of both hazards simultaneously and overlay that with resilience information to determine who is most likely to be negatively impacted by the hazards. This slide is an illustration of the concepts previously discussed on slide 20. It demonstrates the benefit of adding risk and vulnerability information to a situational awareness tool like Disaster Aware. In this instance, we gain the ability to combine the risk assessment data with remotely sensed data for a more focused, complete picture. The RVA can quickly provide a high-level overview of where to allocate resources given deficiencies in capacities or high vulnerabilities. When remotely sensed data are combined with this information, a more clearly defined, actionable picture emerges. This can quickly guide resource allocation and decision support during times of crisis. As part of a subnational assessment in El Salvador, PDC was approached by the Ministry of Health. The question raised was, were Zika cases related to water storage practices? A hypothesis was generated that populations with piped water and/or sewer access are less likely to store water, and stored water was hypothesized to increase mosquito breeding. However, when the case numbers were superimposed on piped water sewer access, there did not appear to be a correlation. But when PDC applied derived products from remotely sensed data, here we see land use, land cover, and we've masked out everything except for urban areas, a correlation between urbanization and case numbers was then observed. And this was important because it allowed the Ministry of Health to reconsider their initial hypothesis and then change their resource allocation away from focusing on piped water access to focusing on these urban areas to determine what was actually contributing to the mosquito breeding and the subsequent rise in Zika cases.
As demonstrated, remotely sensed data are extremely valuable for supporting informed decision-making for humanitarian assistance and disaster response activities during both planning and response operations. For more information on the Pacific Disaster Center, please visit www.pdc.org. And don't forget to sign up for your own Disaster Aware account today.
So thank you for that wonderful presentation from PDC. This brings us to the end of this webinar series, which was Earth Observations for Disaster Risk Assessment and Resilience. We had 4 sessions, and I'm just going to summarize what we saw. We started with NASA remote sensing data introduction and overview. We looked at several data sets from different satellites as well as from Earth system models. Then we had a guest speaker from CDAC, and she talked about socioeconomic data for disaster risk assessment. Our second part focused on assessing risk of floods and cyclones using NASA data. We went through a step-by-step procedure demonstration how to download precipitation data, winds and sea level pressure data, how to analyze this data using online tools as well as using QGIS and also Excel. So how to work with different data sets from different tools and also with different software package that we saw, just so that we can have semi-quantitative information about disaster risk assessment for these two hazards, floods and cyclones. Then last session was about disaster risk assessment case studies, and we had a speaker from New York State Department of Health. She showed how remote sensing data are used for extreme heat or heat stress monitoring, and how they use it for decision making in the state. So that was a very informative talk. Also, we had a number of presentations from World Resources Institute. They showed how their tools, different tools, they help in looking at disaster risk assessment online. All the data, some remote sensing data and socioeconomic data, along with some in situ data, also they all are available through their tools, and we saw that. And today we had a talk from Pacific Disaster Center. They talked about operational application of remote sensing for disaster management. They work with internationally, and they work with multi-hazard situations. So their presentation was also very informative for better disaster assessment as well as better disaster management. We started with all these terminology based on UN definitions, and we focused on disaster risk assessment, in which we looked at hazards, exposure and vulnerability, and then disaster, which combining hazard with vulnerability actually makes it a disaster. That's what we saw. And so that was our focus. We focused on cyclone, floods, and heat index or extreme heat. And as shown here, any disaster risk is really a overlapping between what kind of hazard is there, vulnerability to that based on what kind of exposure is there. So we went through that. So finally, what we want to share here is doing DRA using remote sensing observations have limitations as well as advantages. We'll start with some of the limitations that we saw. First of all, as we saw in part 2, we looked at data sets with relatively low or coarse resolution. They all had different spatial and temporal resolutions. As listed here, immerged precipitation, that is 10 kilometers, half hour. And actually, I have not listed here, but TMP or trim data, that's 25 kilometers, 3-hourly data. MERA2 and GEOS5, these model data that we saw for winds and sea level pressure, the resolution varies from 25 to 60 kilometers grid size, and these data are available hourly. MODIS data for land surface temperature that we saw from NYS, Department of Health, their 500-meter resolution has broad swaths about 23-30 kilometer, their daily data, and NLDAS is 12 kilometer. So these data they used for detecting extreme heat. Socioeconomic data that we saw, so population and some vulnerability data, also terrain data, impervious surface data that we saw, they have varying resolution from, say, 30 meters for terrain and impervious surface to static data for terrain, and socioeconomic data. They have either their multi-year samples, such as global population was every 5 years or so. So everything has different spatial temporal resolutions. And so all this information is there, but So this is not as much limitations of data themselves, but it requires that you have to do quantitative data analysis. You have to work with these different spatial and temporal resolutions and integrate them so that you can analyze them for a given disaster. And actually, in situ observations help also. So combining these remote sensing data, which you have to analyze, and combine them with in situ observations, they are required for accurate disaster risk assessment. So I want to share some information about DRA for flooding. In this webinar, we did not talk about flooding. Actually, we inferred flooding based on integrated or area integrated heavy or extreme rainfall. If you remember, we looked at Houston flood case. We had a box centered around Houston and vicinity. We had integrated rainfall over that region. We looked at time series and how rainfall changed from month to month, and then in certain months, day to day, how it changed. We looked at threshold. We came up with a threshold for defining extreme rain, and flooding was inferred from that. So based on this coarse remote sensing data, it's not possible to look at special pattern of flooding within an urban area. So that's why we use this integrated rainfall. There are certain flooding tools available which look at special patterns, and we did not go into that, but these are available from past ARSET webinars that we will see in a minute. One such tool uses optical images from MODIS and from Landsat. The resolution here for MODIS is 250 meters, so it is moderate resolution, and Landsat has slightly high resolution, 30 meters. These sensors can provide information about if there is inundated surface. You can see through these images, but one limitation is that if there are clouds present, then these sensors cannot see through clouds, and you will not see surface even if it is flooded. Also notice that Landsat, which has relatively high resolution and would be good for monitoring urban flooding, has swath which is not that wide, and temporal resolution is 16 days. So you might miss some flooding events if every 16 days you have one image. There is also SAR or synthetic aperture radar data, which is microwave data available, which you can use for flood monitoring or inundated surface monitoring, and has quite a high resolution, 5 meters, but that also has a lower temporal resolution of 12 days. So these are all the flood tools based on images. One can also use flood models along with routing schemes, but then they are also dependent on weather data, which drive these models. So if you use remote sensing data, say, then GPM iMerge would give you 10 kilometer rainfall that you can use for driving these models. So again, here also you're limited by availability of forcing data. And so DRA for flooding based on remote sensing would require combination of these different tools and in situ measurements. So you can look at multiple sensors, different times, combine in situ data, say stream gauge data or LiDAR data, and also use flood modeling data. So that's a complex process, and also it is regionally dependent. So we did not go into these details, but to know more about these flood tools, you can go through the webinars listed here that talks about all the MODIS-based flooding tool, hydrologic model-based flooding tools, SAR-based flood monitoring, and so these webinars can provide more information about that. And some of the obvious advantages of using remote sensing for disaster risk assessment are listed here. First of all, remote sensing observation, they provide data information where there are no in situ data available. Also, they're especially uniform compared to in situ data. These in situ data are point measurements. Also, they're not uniformly measured everywhere. Not only there are gaps in between, but each sensor from place to place changes Whereas satellite going over entire globe, it's the same sensor that looks at different parameters, so you have uniformity that way too. All these in situ measurements, sometimes from place to place, they have biases and they cannot give you a good global or large scale picture. All the data that we talked about are all open source, freely available, and as we saw, data access and download tools are also available, so they are easy to use relatively. Also, there's availability of near global, past, present, and forecast data, especially for hazards that we focused on today, this webinar in cyclones, flooding, heat index, etc. In addition, we also have exposure and vulnerability data available. So combination of these can improve disaster risk assessment, especially when cannot overlook how important past data are, and also consistently derived past data that give you good hazard assessment at a regional scale. So over any region, combination of Earth observations, Earth system model outputs, such as we saw, and socioeconomic data, and also combined with in situ data, that actually is the way to go for better disaster risk assessment, and that leads to improved overall disaster risk management strategies. So that is the message we would like to leave you with, that these data can be used along with your regional in situ data for improved disaster risk assessment. Just a reminder, before we close the session, 2 homework assignments are due by 30th of August. From the website, you have the Google form links where you can submit your homework, and you will get certificate of completion approximately after 2 months from Marinas Martins. Just a reminder here, this is ARSET listserv, and you can access information about past webinars from here. Upcoming training activities also are listed here. Presentations that we had during this webinar series, they're all available from this site also. And we really want to thank all our guest speakers. From CDAC, we had Susanna Adamo. From New York State Department of Health, Tabassum Insaf. From WRI, we had Corey Philo, Liz Sakachia, Emilia Snyder, Samantha Kuzma, Leah Schleifer, and Emily Nielsen. And from PDC, we had Michael Chapman and Joseph Green. So thank you all for your time and effort and information that you provided through this webinar series. And thank you all for participating in this webinar series also. One last thing is that you will be receiving a survey from us. ARSET always has end of webinar survey questions, and we request that once you receive that survey link, please fill out the survey. So that's your feedback to us about our webinar. We always like to improve and see how we can do better in our webinar. So your feedback, your comments are extremely important to us. So you will be receiving a survey link shortly by email. So please fill out the survey as soon as you can. And thank you for attending this webinar series. And we will have question and answer session now. Thanks. Okay, well, thanks again for presentation. And we have Michael Chapman here online, and he can answer some of your questions.
Aloha from PDC Maui, and thank you for having us. We did see some questions coming in through, looks like the text messaging portion. So we are addressing those as they come up, so thank you. But if you have any questions, please let us know. Law.
Okay, so moving to question 1. This looks like it's already been answered, but where does PDC get its socioeconomic data, and how often do they update this data? And the answer is the socioeconomic data comes from a variety of sources. The global assessments come from the World Bank, academia, and the World Health Organization. The data are updated once per year. Subnational assessments come from the specific countries. These are obtained through bi- and multilateral engagements with the countries. These are updated when the specific country update their data. Question 2. What platform does PDC use for their data processing? Can governments link to their data in a distributed GIS system such as ArcGIS Enterprise? The answer. PDC uses a variety of platforms for processing data, to include ArcGIS, proprietary and open source software. For information, you can click on the link below to get more answers to that question. Question 3 refers to slide 18. Which data sets are used for subcomponents on that slide, and are they publicly available? Michael, do you mind taking this?
I'll hand this one off to Dr. Joe Green. Yeah, so there are actually quite a number of subcomponents, probably too many to list here, but the subcomponents can be accessed via emops.pdc.org. We have full metadata on those. They're available to kind of explore and kind of delve into in a little bit more detail. And all of the indicators for that particular slide should be publicly available. What we attempt to do with our global risk assessment is to leverage publicly available data so that there are no use constraints. Users can then take the assessment and kind of adapt it for their own uses.
Great, thank you for that. So question 4, how does one create region-specific climate indicators from satellite or reanalysis information for a region, such as the islands of the Caribbean?
Okay, so I'll go ahead and, this is Joseph Green again. I'll go ahead and take that one. So this is actually something we're looking into leveraging more and more. It's a very good question. It's a very astute question. The issues with the islands of the Caribbean are that the publicly available data are sparse, largely because of data collection constraints and the fact that a number of the Caribbean islands themselves are territories of larger nations. And oftentimes, their available data are just aggregated back into, for example, the United States or France. So satellite imagery, doing derived indicators there are kind of the next step that PDC is looking at leveraging. What we are looking at doing is taking both short-term and long-term satellite observations and looking at specific, what's the word I'm looking for? We're looking for any type of change over a time period with things like precipitation, temperature, so any type of anomaly that we're noticing, we're taking that information and then where available, combining it with socioeconomic data. This is, again, something we have just started working on and collaborating with a number of organizations on. So I would say stay tuned for that one. And that kind of feeds also into question 5. And I'll go ahead and take that one as soon as you have the answer fully typed up there.
Okay, so question 5, how best can a drought resilience framework be developed? And if there is any insight into that from PDC, that would be great. But there's a link I have here. It's from UNCCD. It's the Center for Combating Drought, I believe. And there is a report here. The link will be typed. We made available. It talks about how to develop resilience to drought. U.S. government also has a drought program that helps with developing resilience policies, and I'm trying to find that link for you as well so that you can go through that. There are several components to that because drought affects so many different sectors. This is another link from drought.gov. Okay, question 6 is how is the MODIS rasters translated to 12-kilometer resolution in NLDAS resolution? If you see from Tabassum's talk last week, actually it was the other way. They had NLDAS grids at 12 kilometer, and then within those grids, they looked at MODIS data. So actually, just the details were filled in from MODIS. So it wasn't like translated, but in each 12-kilometer grid from NLDAS, MODIS data, the temperature was displayed. So to see details within that grid. But for temperature, you could, if you want to look at everything at 12 kilometer, you can just do raster averaging over that 12-kilometer grid from MODIS. Question 7 is how does one work with data having multiple resolutions? So that's where two things can happen. If you either you can use some kind of interpolation or upscaling or averaging at the lower resolution from high resolution data for your raster analysis to put everything on the same resolution. Or you can look at area integrated information where you are averaging all the data over given area, and that gives you integrated picture. And then you're not working with different resolution, just working with average number over some area. So depending on the application, you may have to do analysis accordingly. Are there any tools to use real-time data from sensors, comparing them to satellite real-time data? What is the platform for such analysis? Tools to use. So I'm not sure exactly what the question is here. But what you're asking is there any near real-time validation going on? If that's the question, there is no platform that does that. I'm not aware of any platform. There are groups, they do instant bias correction in real-time data based on past data. But whether there is any such comparison can be done, I'm not aware of any such tool.
Aloha, this is Michael Chow from PDC. So not looking at the automation part of this, linking the two, but maybe as a side note, through Disaster Aware that you saw during the presentation, we do bring in a variety of different data sources, whether it's static GIS layers or remotely sensed imagery or observations as demonstrated, as well as where the data is available, live information such as stream gauge readings, or other information, depending on the availability from the source or the sensor. So from there, even maybe there's not maybe an automated linkage to doing the analysis to link the two. You can have, for example, the NASA iMerge rainfall data up with, for example, some river stream gauge information to kind of to enhance your situational awareness for that particular event. But just one example. So I encourage you to get an account through Disaster Aware and take a look at the data available. Thank you.
Next three questions are for PDC as well.
Hello, Michael again here. So let me see. For that, the question is, for number 10, does PDC have a standard for their metadata on their data sets? The answer is yes. We use we typically use the ISO 191, so we do use a standard, well-accepted practices for metadata. And then, as Dr. Green said, all of our data layers have metadata associated with them, so you know where they come from, any restrictions, how they are processed, and contact information, and so on, through that ISO 191 standard. But for additional information, we shared that link earlier, which is through our PDC. It's our GHIN, I think it's Global Hazards Information Network, which is a page you can go on and see more information about specifically what data is available and linking to that. But again, if you go to disaster aware, or emops.pdc.org, that's the URL we shared, and once you get an account, you'll be able to access over 4,000 layers through this system and see their metadata and get additional information there. Thank you. For the next question, what is the risk and vulnerability assessment RVA data? I'll hand it over to Dr. Joe Green.
Yes, so that is what we refer to as the collection of our socioeconomic hazard exposure data, governance indicators, and infrastructure data. So these are the individual data sets that together make up our overall risk and vulnerability assessment, which we have the publicly available data sets and also the derived indicators that we have created from those data sets.
Okay, it looks like question 12 is also for PDC, so if you could go ahead. As a government agency, we would like to know if you have any requests to link with your services, any special data agreements needed between parties.
Aloha. Yes, thank you. We do. We connect with, we have projects all around the world, and, at different varying levels, from local, more provincial, state, or national, or international, regional. So we've worked with partners of many types and have had agreements with data sharing. It's something that our data team has been revisiting. Is this what's particularly what's involved or what's included in those agreements, types of agreements, and what's shared externally. But yes, it does. These kind of platforms do exist. If you have any questions on how to if you'd like to enter into or look into having an agreement, a data sharing agreement, also look into that URL we shared earlier. But if you have any specific questions and you'd like to get connected with one of our data leads, please notify info@pdc.org. That's info@pdc.org, as you can pass your question through there. Thank you.
Hi, this is Joseph Green at PDC here. It looks like question 8 was not answered, so I just wanted to make sure that we had a chance to discuss that one and answer that. The question asked, the Nicaragua analysis shows a boundary with very low on one side and very high on the other. Can you please explain the absence of a gradient? Absolutely. So when we calculate these assessment indices or indicators, they are on a scale, so a gradient could be used. This was actually broken down into discrete bins specifically for use by emergency managers. So they could see high versus low, very high versus very low. So in this case, this is an example of how we take our assessment and we tailor the end result to the request of the stakeholder. The Nicaraguan government, the National Disaster Management Organization there, wanted to see the data displayed in this manner. And that, again, goes back to our talk that we gave. Actually accessing this in disaster aware allows you to you can see the breakdown as it was applied, but you can also go in and look at the data itself and see how actually it could be, a gradient could be generated from that.
Thank you so much for taking care of that question. Somehow we missed it. So if there are no more questions, we like to thank everyone, especially from PDC, Michael Chapman and Joseph Green, for their presentations, their help and effort and time with this webinar session. This brings us to the close of this webinar series. Two things. As I mentioned earlier, there is homework that you can upload or answer through Google form on ARSET website, and you will be receiving a survey that please take a few moments to reply to those questions. We want to thank our ARSET, on behalf of my ARSET team, for attending this webinar. I want to thank my colleagues Sean McCartney, Elizabeth Hook, Selvin Hudson-Odoi, Brock Blevins for helping in organizing this webinar and in several ways. And thank you all for attending this webinar series. So thanks everyone.